matrix, and so basically I cannot draw it here, but if we are using both x that means vector, using capital X means a matrix. So for the parameters, we mostly use Greek letters, theta, lambda, and so on and so forth. And our index, so basically we try to use sub-index. Okay, should I speak louder? All right, so we are using sub-index to represent different variables. For example, this is variable 1, variable 2, and so on and so forth. And when we have different observations, we use superindex. All right, so let's start with a running example. So let's say that you went to a casino, and the game is very simple. The casino has two kinds of dice. You flip the dice, gives you one of the numbers 1 to 6. And one of the guy who's running the casino has two kinds of dice. The fair dice and unfair dice. The fair dice, the probability of each of the faces is 1/6. And the unfair dice, the probability of getting 6 is half, and the rest of them is half. Okay. So the game runs like this. You bet $1. You roll the dice, and the casino player roll the dice, and the highest number wins $2. Very simple game. Okay. Now start playing, and you see this chain of numbers on a top. 1, 2, 4, 6, 6. You guess, well, it's suspicious. I don't know why he's winning too much. There's so many 6 in there. So you start asking questions because you don't know. You are assuming that you are started getting suspicious that there might be two kinds of dice. So we are going to use this as a running examples, at least up to the middle of the course, to the middle of this session, and explain different types of graphical model using this context. So let's ask different questions and see how graphical model can be used to answer this question. So you might be given this chain, and you might say that, well, the normal dice can also give you 6, right? Unnormal dice can also give you 6. How far on the tail of this distribution? How far on the tail is this distribution of having two fair dices? So that is the probability. That is basically what is called evaluation. So basically, given this sequence, you want to compute the probability of this sequence given both dices are fair, right? So that's basically, you don't know the model, and you are playing one after another. That's problem of evaluation. Now let's say that you did this, and then you realize that, oh, this is too far on the tail of two dices being fair. Now you want to ask this question: that how many times this guy is using unfair tie? Like, is this a strategy? Like sometimes can use fair ties, sometimes can use unfair ties. What is the proportion? How risky he is in terms of using this? So this is the problem of decoding. You want to do some inference that there is a model that this model says that like an unfair casino, and you want to compute that what is the probability of using unfair dice given the model that you have of the world. We're going to build this model in the following section. Another question is that, well, so in the previous section, somebody has given you that, hey, he's using unfair dice, and the probability of that unfair dice is 50% 6, the rest of it is 50%. But you may not know that, right? You may only want to say that given this, and given this extra information that there are fair dice and unfair dice, I want to find out how unfair his unfair dice is. That is a problem of learning. So basically, you don't know you want to learn, given the data, you want to learn the status of the world. So these are more or less aligned with what I told you in the last session about the three different paradigms in PGM and different modules of the PGM. So now, so let's start engineering this observation and build it. So what do we have here? We have some observed value. So we have the sequence of the dice, 3, 4, 6, 6, 2, 1, 6, 2, 6, and so on and so forth. This is what we have observed. Let's call that y. I'm going to use circles. So this is y1, y2, y3, and so on and so forth. This is y is the value of the dice that I've seen. Now, this is observed. What is unobserved? Yes, exactly. So which dice is used? So it's basically he's picking one dice and flipping it. So let's call that x. x1 is that. So what is the status of this? What are the different status that it can take? If it is exactly. So it's like so it is fair, unfair. Another one for this. So every time corresponding to each observation, we have one of these fair, unfair. Okay, so this is unobserved. You don't know which one he has used. So now, all right. So what is the relationship between them? So if you want to encode it probabilistically, this is generating this guy, right? Like the dice, fair or unfair, generating your numbers, right? So this is a way to relate these two random variables together. So this relation of unobserved, so this is a very simple example, but the general idea is that you have some unobserved and you have some observed data, because without observation, how do you want to learn the parameters? So that is producing the sequence that you have seen. Now, is that the only structure that we have? So what about the relationship between xi and x2 and different strategies? So let's say that the guy who's running the dice has a strategy. So for example, you are flipping the dice and he's flipping the dice, and every time he's a strategy that, yeah, if he gets a high number, I'm going to use the unfair. If he gets a low number, that's fine, I'm going to receive. Right? So that will result into what? What kind of arrows I have?
Y1 would, there would be an arrow from y1 to x2, y2 to x3.
I would suggest this, because he knows what is fair or unfair, right?
No, but you said that if the rolled number is high, then you switch.
Okay, fair enough. That would be, so basically you are saying, you are suggesting this. You are suggesting this. So now, but for a running example, so let's say that he knows that he has given you fair dice, and he's only making decision on his own. Right? So I'm going to say that I'm the Causal runner. I'm just giving the fair one, and I just make a decision based on the fair, on the dice that I've given. So that will produce this kind of graphical model. That might be a little bit more convolved too. So for example, I might think into two decisions before. So if I look into two decisions before, I have to go and do something like this, right? From the previous examples. So, so that will result into the general structure of the graphical model in very simple word example. So in this case, this will result in what is called theorem Markov model. I'm presuming that you guys have already taken machine learning, so you have seen this probably in the machine learning class. And it can find application in a large spectrum of data, for example, to model a data sequence, phenom in modeling of the language, and so on and so forth. So during this class, we are going to study objects like this. That there are arrows between the random variable that is basically conditional probability distribution, and arrows from unobserved random variables to the observed one that's basically helping you to get an insight from the data. So remember we talked about decoding, asking different questions. So what are the insights that we can get from this? So let's say that is your model. So can anybody tell me how I can write this joint probability distribution of Px and Py? This is your structure. We talked about it last time, that how we can, given this structure, how we can write the joint probability distribution. Anybody want? Yeah, please.
The product of probability of yi, all the product together.
Yeah. So yeah.
And then the product of.
So the probability of py1, py2, or.
Yeah.
And then.
And then px1 given y1, px2 given x2.
Okay, so you're saying that py1, py2,
wait a
py.
second. That's wrong. Py2 given y1.
Okay, yeah. So all right, so we have to have py2 given y1, py3 given y2, and so on and so forth. We still have to have py0, py1, and what else?
The x1 given y1.
Exactly. So that will be this one, right? That's a natural factorization that comes from this graphical model. But of course, I mean, so this is the natural factorization that comes from this graphical model. But of course, I can use chain rule and come up with different graphical model that they may not exactly comply with this, but so it means that like, I don't know how to fill in each of these conditional probability distribution, but this is the natural one. Another way of writing the same thing is basically this. Here I haven't assumed anything, it's just a chain rule, right? Here just, I'm saying that x is x1 through xt, and y is 1 through yt. I can use simply chain rule. But the thing is that because this is very general, it doesn't assume anything, I don't know how to unpack this in the same way that I unpack the factors that are coming from graphical model. So now let's go back to the question that we asked at the beginning. So if you want to ask the question that how far on a tail is this sequence that you have observed in the casino is on the distribution of the fair tails, that will boil down to computing this marginal probability. Evaluate the probability of a sequence that is x. And to do that, we have to integrate out all of the y's. And how to integrate all y's, we can simply plug in this variable. Now, note that if you didn't have this structure, you should have only used this chain rule, right? And if you wanted to only use the chain rule, so let's say that you have t dice, how many elements is going to have in, how many elements you would have had in this summation? 2 to the power, so you have exponential number of summation. The advantage of having this kind of a structure is that you can show that when you have a structure like this, these sum can be computed polynomially. Because otherwise, if you don't assume anything, you have to sum 2 to the power of t terms. And that's computationally expensive. So that graphical model helps you to compute this marginal that gives you an insight. How far on the tail is this casino from fair casino? Another question is that, like, let's say that you know that it's unfair, he's using unfair, and somebody has given you the unfair value of the dice. You want to see his strategy. You want to see that, well, what is the proportion of unfair tile given some observation? Because you haven't observed this one. And you want to see basically what is the probability distribution of using unfair tile given the sequence that you have. So we can simply use the Bayes rule that this TXC is basically this joint distribution that we got from these. And this is our marginal, and compute that and give insight about it. So what is this? Hopefully this gives you enough idea how what is undirected graphical model is, but to be a little bit more formal, undirected graphical model, or what is also known as a Bayesian network, is basically sequence of, is a network structure that the node represents random variable, observed or unobserved, and edge represents conditional independence between them, or relationship. So one can view a Bayesian network as a data structure or as a language to encode the condition to encode in conditional independence. For example, if I have this graphical model that x and y's are independent, that means that, so if I know they're independent, so px and py can be written as a px by py's, and it also encoded into this simple graphical model. On the contrary, in this case, when y is dependent on x, the joint probability distribution of px and py can be written as px multiplied by another factor that's a conditional of y given x. So in other words, there's a one-to-one correspondence between this conditional independence and the graph structure. So saying this, so showing this graph is equivalent of saying x and y are independent. And showing this graph is equivalent of x and y are not independent. So another advantage of undirected graphical model is that you can view these as a way to generate data. So you can start from the ancestors, so which are basically the nodes that are on the top, and follow the chain of the command in the Bayesian network and generate data. So here is an example. So let's say that this is the grandparent of all of these nodes, and it has two children. So you can sample from that guy and put it in the conditional and sample from these two. And this random variable has only one child. So after you draw a random variable from this one, you can draw another one from this one and plug that in to draw the final random variable from the final. So this will give you a strategy how to draw a sample from the joint distribution of these 6 random variables. Because otherwise, it's a 6-dimensional entity, right? So this will give you, say that, hey, first draw from one, and then from these two, and then this one, and this one, and then you have 6-dimensional. Is that clear? Okay. So what is the theorem behind it is that, well, for a given directed acyclic graph, which is basically a tree structure, there is no cycle. The most general form of the joint probability distribution can be written as a joint probability distribution of all the random variables can be written as a set of conditional. So to give you an example that I showed you that, in the previous graph. So let's call this one x1, x2, x3, x4, x5. So in this notation, the parents of x2 are what? It's a set, right? What is this? What is the parents of x2? x1. And what is the parent of x5? 3 and 4, right? 3 and 4, right? So I can use this to write this joint probability distribution. So the joint probability distribution of this would be what exactly?
E of x1, E of x3 given x1, x2 given
x3 given x1 because it's its parent.
x2
And
given x1,
x2 given x1.
x4 given x2, x5 given x3 comma x4.
Right? So, and the theorem says that that's the most general way of writing this probability distribution given this graph structure. I have to say that this is very, it only specifies a family of the distribution that satisfy the conditional independence in this graph. And we're going to see more about this in the following slide. But basically, a DAG gives you a family of distribution that satisfy a graph structure. It doesn't give you a specific parameterization that comes next. That basically comes into how you specify each of these functions. So here is an example. I think I showed this example in the last session that there was two receptors and there were a bunch of enzyme here and there was something that regulates this enzyme and that results into how the genes are produced. So let's say that you talk to your clinical collaborators or a doctor or a biologist friend and is giving you this. And so that boils down the joint probability distribution of all of these variables, the amount of material that of these specific minerals in your cells and the amount of enzyme produced in your body and how this regulator acts and how much of the genes are produced in your body. So you can write as a joint probability distribution following the graph structure. Now, how we can specify the structure of the undirected graphical model. So when you want to build an undirected graphical model, there are usually two steps. The first step is qualitative step. So the qualitative step, you basically draw the conditional independence between different random variables. That can come as you talk to your collaborators, or you have some ideas that, for example, this variable causes the other variable, and it's coming from your domain knowledge. This is very qualitative. That will result in the structure of this graph. And the qualitative part is coming, so that will give you only the family of the distribution, while the quantitative part comes into giving you one probability distribution based on the conditional probability distribution that you have. So for example, so in this specific graph, F variable depends on C and D. So the conditional probability distribution of F depends on two variables, C and D. So for a second, assume that F can take two variables, and each of those can take two variables, right? So CPD will become a table that based on each of the values of the CPD, you will get a distribution. So the row sums to 1. Is the notion of CPD clear? Okay. So now one question. So if I give you a table of, let's say, 4 by 4, say that this is variable x, this is variable y, and have some values. Just by looking at it, can you tell me this is CPD or joint distribution? How would you do that?
Because each of the blocks will represent probability of x comma y rather than.
So either it's row sum to 1 or column sum to 1, but it's a joint distribution, the entire elements sums to 1. Okay. Now, as I told you, how the structure of this is qualitative part, how the qualitative comes from. So either it's coming from your domain knowledge, or you can learn it from the data. Of course, learning from the data can be a little bit risky, and we talk about it in the learning section of the course. But these are the different ways that you can build your general graphical model. Either it's coming from your domain, you learn it from the data, or you build it, because it can be very big graph, you can build it as a module. So you have a module that, let's say that this module does clustering for you. And you think that, oh, part of my data should be clustered, so just plug that in and connect it. So either you build it in a modular way, or you build it in coming from your domain, or you're getting it from the data, or some combination. So hopefully by now you have seen enough that, well, we have some ways of coming up with this Bayesian network, but there is very close connection between Bayesian network and conditional independence. So in the following slides, we're going to talk about conditional independence properties. So let's, before getting into more detail, let me tell you the motif of the graph structure that you see in the graph model. So at the end of the day, you have a DAG, and there are a bunch of arrows going to each other, and of course it should be DAG, so it shouldn't be any loop in it. But at the end of the day, you can explain any directed graphical model or any Bayesian network with a motif that keeps repeated in your data. And overall, there are three kinds of motif in a data. The first motif is this decoupling, that there is a common ancestors that produce two random variables. So an example of that is that, for example, there is there's a high-level phenomenon that results into change in a variable B and a variable A and variable C. That is called decoupling. So if you know A, if you know B, the value of the B, you know how A and B are influenced. So that is called decoupling. Another motif that you see in the data is a cascade. So the cascade says that, like, think about it this way, for example. I see, let's say that somebody started smoking, and fire went on, and fire department showed up. So there's a cascade of the event that first this one happened, and then this one happened, and then this one happened. So if the one in the middle does not happen, doesn't matter what happened before, that stops the event. So that is called a cascade, that basically knowing B decouples what you observe in A and C. This is another motif that you see in Bayesian network. The most fun part, basically, is the V structure or colliding. So to think about this one, let's say that I'm going to define something for A and B and C. So let's say that C is my car engine works or not. My battery is functional or not. My gas tank is full or not. Right? These two have nothing to do with each other. I might get the car with the empty tank or with not empty tank, or the battery, my battery may be working or not. But the fact that my car, to get my car to work, I have both of them functional. I should have my gas tank full, and my battery working. So although these two are independent, if I tell you that, well, today my car didn't work. So if I tell you my car didn't work, you probably say that either your gas tank is empty or battery is not working. So that is called V structure. Basically, if you know the event that's happening at C, which is at the colliding variable, or the V structure around the variable, then these two become dependent on each other. Is these three motifs clear? Okay. So we are going to use these three motifs to build our general structure. I mean, of course, this doesn't have to be two. This can be A, B, D, and this doesn't have to be like this. It can be A going through B, and then going through Markov C. But you get the idea. Basically, the general motif hasn't changed, right? So there's we don't call this one, like, say, size structure. It's still V structure. Okay, cool. So this is basically a compact way of representing graphical model, and this will help us to decode the conditional independence that the graph represents. So let's start with one. So I told you that given a graphical model, so there's equivalence between factorization on a graph, the way that you represent a graphical model with the factors that's coming from your graphical model, and the conditional independence. Okay. So in this one, let's start with one of those motifs. So this was the common cause motif. So the B is causing both A and C. So as I told you earlier, that if I know B, I don't need, so A and C are independent because this B is caused by these two. A and C are caused by B. So So I can write a set of, introduce this set later on more formally, but the set of conditional independence as a set that has only one element. A is independent of the B given C, and I want to prove that if I write the joint probability distribution of these three as this factorization that's coming from the graph, these are independent. Right? So, yes?
A, are B and C mixed up in the I of G?
Say it again.
Are B and C switched in I of G equal?
Oh, you're right. Yes, that's my mistake. I'll fix this. So it's basically A and C are independent. Sorry for that. Okay. I think my factorization was correct, but this one. Thank you for reminding. So how can I go with the proof? This is very simple proof. So how can I prove it? How can I go with the proof that these are equivalent? Any idea?
Base.
Okay, so how can I do it?
So probability of A giving B is the joint probability of A and B
Joint probability of A and B.
over probability of A.
So let's just start with this. Let's just start with, so what is another way of writing this? So let's just start with that. Another way of writing this one is that P A C given B is what?
A given B
Right? That's the same thing, right? So if I prove that, I'm done. How can I prove it?
probability of A, B, C is equal to probability of A, yeah.
That's the one on the top.
No.
Okay.
So the left hand side by Bayes rule you can say it's
Okay, so let's write this one. So I can write that P A C given B, use Bayes rule, is P A B C.
divided by B.
Okay. And I can substitute that in from the factorization on the top. A B C B and D B and like that, right? It's very simple. So what about this? This is also, can I say P A B conditional C can I say that?
No.
Why not?
Because we just established that they are dependent.
Yeah, so this is it's called VS structure. That's basically, although they are marginally independent, if I know something about C, they are not independent anymore. That's my card not working. Right? So now it's time to introduce that curly I that I showed in the previous slide. So that's called Imap. So in the next 3 classes, you're going to see a lot of Imaps. That's basically set of all conditional independence by a probability distribution. So the more formal definition is that if I have a probability distribution on X, X is all of these random values, X1, X2, X3, and so on and so forth, right? Doesn't have to be univariate, doesn't have to be multivariate, there can be all kind of crazy. So the IP or Imap of the probability distribution is set of all independences that are coming in the form of xi and x independent of I given z. So I'll tell you what those x and y and z's are, regardless of how we set the parameters. So let's say that if I have a very complicated Bayesian network that goes to here, goes to here, this goes to here, and so on and so forth. So x is X is a set of nodes. So is Y, and so is Z. These are set of the nodes. So you can pick out randomly set of the node and say that condition on Z if X and Y are independent. Right? Okay. So now, how many? So if I have a graph of n nodes, how many different ways I can build that X condition on Y? X is dependent on Y condition on Z. How many different ways I can build? Let's say that I have a graph of n nodes. How many different ways I can enumerate that? Enumerate this guy. Yes.
More than 2 to the n?
Let's say it again.
More than the power set 2 to the n? Because
Yes.
you can have every possible set of things with a divider between.
Exactly.
Yeah.
So it's going to be, so the set of possibilities to test is gigantic. So it's basically the number of different ways that I can choose X is 2 to the power of n. And then the other one is also 2 to the power of n. And the other one is also 2 to the power of n. I mean, of course, we have to make sure that X and Y's are not the same, but order-wise, that's that big. So this is basically, if you have an algorithm that you query that, like, this is my X, Y, and Z, are they independent or not, that basically can build this Imap for you. Make sense?
Can they have a non-null intersection, X and Y and Z?
That's okay, it can become null. So that's actually a really good question. So, okay, let me give you an example. So in a VS structure that I showed you, so in this one, X, okay, so let's call this A, B, C. So one, you can ask this question that A is independent of the B condition of nothing, which is basically as if you're splitting Z. But what would you do here? So what is this? What's the answer to this? Condition on nothing. Are they A and Y, A and B are independent? So the problem happens when I condition on C. So, all right, so that's the definition of Imap. So given a probability distribution, which means that you know it's not just the graph, you know the values. The Imap of the probability distribution, which is a specific manifestation of the graph, is called Imap. And for any graph, the Imap, so the I of the K is basically probability distribution that are induced by that graph. So that is a little bit mouthful. So let me give you an example. So I told you that when you define, when you are given a DAG, that will only, so that will give you basically a factorization. How we can write the joint distribution as a different factors, the multiplying different factors. That's basically gives you that. But that will only give you the family. You haven't specified the parameters, right? You can choose the parameters however you want, as long as they are CPDs. So there is a difference between, this is why it's written as a subset, that if I am given a graph that basically induces a set of independence, that is a subset of all of these all of these independence that are in a specific distribution that belongs to that family. I'm going to give you examples in the following. But hopefully the notion of Imap is clear. If it is not clear, stop me because we are going to rely on it. Is the Imap clear what Imap means? If I give you a probability distribution, it's basically you can randomly choose a set of random variables in that joint distribution, and will give you the set of independence that are satisfied by the probability distribution or not. That's it. This is a little bit mouthful, but that's basically what it is. Is that clear? Should we move on? Right. So, all right, so as I told you earlier, a DAG gives you a family of the distribution, not the specific probability distribution. Now, the question is that we have three graphs. One, that there is no arrow between X and Y. All right. The one that an arrow goes from X to Y, and the other one goes from Y to X. And I've given two probability distributions. This is a table. This is a joint table, right? This is when x get the value 0, and y get value 0. When x get value 0, y get value 1, and so on and so forth. It's like each of those get 2 states. It's binary. And this is the joint probability distribution, so sums to 1. Okay? Is that clear? So this is one probability distribution. This is another probability distribution. Now, my question is that between these three, which of these three allows both of these P, Py, and P2? Any idea? Just so as a hint, look at the numbers. Like the number should give you something. So my question is that, so given a probability, so I've given you a specific table, and I want to see whether I can fit in this table to both of this graph. I can find a parameterization of the CPD that is one parameterization, this is another parameterization. Any idea how to approach this? Yes?
Build a contingency table. So the marginal probability of x being 0 is 0.4. The marginal probability of x being 1 is 0.6. Marginal probability of y being 0 is 0.2. Being 1 is...
It's a good observation. So we are saying the marginal probability of x here is 0. So the marginal probability of x being 0 is what? 0.4. So if I write it for you, it's going to be, so let's just start with this. So let's just start with set of conditional independence. So what is the Imap? So that's a good intuition, we'll get there. So what is the Imap of this graph?
X is independent of y.
Yes. What about this one?
No.
Okay. What about this one? So basically, this one says that this graph only allows x and y independence, while this graph doesn't have anything. Doesn't mean that it disallows it. It means that a probability distribution, so because MT is a subset of any set, right? The subset of any set. So a probability distribution that fits into this has some conditional independence, and of course this is a subset of that. But only probability distribution that x and y are independent are combined with this. So if you write the marginals as you mentioned, so the marginals of Px here is this. X1 being 0 is 0.4, and this being 1 is 0.8. And for y, and for y,
0 is 0.3.
exactly. Right? If I multiply them together, so let me define it this way. So this is the marginal. I can define my marginals in a way that makes this guy happy and get the same probability distribution. So it means that these two graphs can generate this and this, while this graph can only generate this. So if you write this down, you realize that with these these marginals, you get this. Right? So this table is only compatible with this graph structure. While with different set of the CPDs, with these two, I can get both of them. So why did I give you this? Because I want to show that given a graph, you are only giving the conditional independencies. This is a conservative say of, well, I want to limit myself in a family that these conditional independence are satisfied. You can play with the number to fake extra conditional independence. But the set that I give you is only a subset. It's not all of the things that you'll give. Is that clear? So this is why in the previous slide we had a set of conditional independence that are induced by the graph and a set of conditional independence that are induced by the probability is that this is a subset. Makes sense? No? Okay, so, all right. So can you give me, okay, so which part of that I should explain to make it sense? Which one you have question? Yes?
Can you explain how marginals are related to I of G?
How marginals are related to what? Ah, so the I of G's are given, okay, so the I of G is coming only from the graph structure, so it's not dependent on any specific parameterization. This is a parameterization, right? This is another parameterization, right? So to write I of G, you only look at the graph. You don't look at the parameters. To get the IP, you have to look at the parameters. This is why this is a subset. Yes.
So the I of P for P1 would be X independent of Y, and then the I of P of P2 would be the null set?
Yes.
Okay.
Yeah. Exactly. Yes.
What is IFP? I remember you defined it for graphs, but not.
No. There's the I of G,
So,
which is for graph, and there's an I of P, which is for specific parameterization problems.
Okay.
Make sense? So, to summarize, these will give you, this will give you a parameterization for the graph, and the other one will give you a parameterization for them. Okay. So now, the intuition behind independent set is that for given factorization, so this is hard to understand. So because this set of x and y are independent from each other, there are so many ways to set it up. So let's get something which is more intuitive. So the one intuitive way of saying that is to define it as a local independence. So if I have a graph structure, set of non-descendant, so for example, let's say for this guy, so this is a parent, and so this is a descendant. So if you have something here, this is a non-descendant, right? This is the co-parent of this child. So the local, the local set of independence, which is a subset of IG, is basically says that xi is independent of the non-descendant set given out of the parent. So in this specific case, if I know this parameter, this random variable, the parent of this, so if I condition on that, I'm independent of this guy because this is not a descendant. Of course, this is not going to give you all sets it's not going to give you Imap, but it's going to give you an intuitive, a subset of those that you can understand. So another important notion here is deseparation and deconnection. So bear with me, this is a little bit mouthful. So the formal definition as follows. For a set of x, y, and z, which is a subset of the elements of the graph, a joint distribution is followed that if x and y are deconnected by a subset z, if I find a path between them, and anything that are any elements of, so either one of the elements of that path is in set z, or one of its descendants on z. So if that happens, we are saying that set x, set y condition on z are deconnected. So give you an example. So let's say that we have three sets, x, z, and y, and I find a path between them. If one of the elements of this guy fall into set z, they are deconnected. It is also possible to have something like this. So the path goes through another node, and one of the descendants of that node is this guy. That is also means that these are deconnected. So they are separated if all of the paths that they are, so if they are, so this is another case that for this specific path, the sets that there's a, so if you have things like this, that there's not V structure, that is okay, right? So,
Is there any condition on Z to be observed or unobserved?
well, you are conditioning on it, right? So you're like as if you're observing it.
What
So,
is a collider?
huh?
What is a collider?
So the collider is a V structure that I told you. You remember? So this is a collider.
Okay, so
Yeah. So basically, they are deconnected. If I can find a path, so undirected path, forget about the arrows. If I can find a path between them, if there is a collider, that should be either in Z or one of its descendants should be in Z. If you have case like this, they are deconnected. Otherwise, and they are separated if they are not deconnected. So if that happens, we are saying that X and Y are independent condition on Z. So, well, this is hard to understand in the sense that, like, okay, so if I'm a computer scientist, give me a set of X, set of Y, set of Z. How can I write an algorithm to say that this one is satisfied or not, or this is an Imap or not? So to do that, we are going to show you an algorithm in the next slide. But let me give you another alternative definition. So another way of defining the same thing is to do a so-called moralization. It's a little bit funny name, but let me give you what it is. So let's say this is a part of the graph, and you want to see if X and Y are deconnected. So you're going to moralize this graph. So what is the idea is that, okay, so there are two parents for this child, but they are not connected to each other. If you're a religious fanatic, you say, okay, that's not acceptable. I'm going to connect them. I'm going to marry them. All right, that's called moralization. Like, it's more moral than this one. They are married, but they're not married, but they have kids. So that's called moralized graph. So moralized graph is this undirected graph that all of these V structures, all of these parents that are not connected to each other are connected. So now, given this conversion of original graph to the moralized graph, if I find a path from X to, if Z blocks all of the connections between them, they are separated. So in this case, because they are the parents of the same child, they got connected, so there's a still active path, so I can go from X to Y. Remember that I removed the arrows. So there is a formal algorithm to test general structure that, like, if you give me a subset of X, subset of Y, subset of Z's, I can basically compute the answer of this test that are they independent or not, and that's called Bayesian baseball algorithm. So the ingredient of the baseball algorithm is as follows. So remember we had three motifs. The first motif was the causal trail. So this is a chain that goes from X, Y to Z. If you condition on the one in between, or the one in the middle is observed, the ball cannot roll to go to the other side. But if it's not observed, the ball can roll in. Right? So this is block path, this is the active path. Another case is a common cause. So these Y is a common cause of X and Y, and if it is observed or it's conditioned on, the road is blocked, so the ball cannot roll in. But if it's unobserved, the ball can roll in both sides. So remember that it's irrespective of the direction, right? The ball can go this way, it can go this way. So is this way. It ignores the arrows. The third motif that I show you are this collider or V structure. So if X and Y are both parents of Z, X and Z are both parents of Y, the road is open if the y is in a subset that you're conditioning on, or that it's observed. The ball can go here, can go here. But if it's unobserved, the ball is blocked. So is for any of the descendants of these two. So if I give you, so basically give you this structure, and say that this one is observed. So now my question is that, does x independent of y condition on w? What's the answer to that? Huh?
False.
Yes. So because it's basically this. So this will give you an algorithm to test queries like this. So let's play with an example. So what is the answer to this one? I have this graph structure. Does A and E are independent given B? How many people think yes? How many people think no? How many people yes? How many people no? Okay, good. That's true. So because if I observe on, if I condition on B, I cannot go to E, right? There's no way. All of the roads are blocked. Okay, what about this one? How many people think that's yes? How many think it's no? How many people yes? Okay, how many people think it's no? Okay, can somebody explain why no? Yes.
If you moralize the graph, then A and E are connected. That's the simplest way.
Okay, that's the simplest way. Fine. So if I A and E, so how can I moralize it, by the way? Whom should I connect? Whom should I marry?
A and E.
A and E should marry. Why?
Because they are the common parents of D.
Okay. Anybody else?
B and D.
B and D should be married. Okay. So if I condition on C, I can still go to E, right? I can still go. Okay, sorry. My bad. I can go to this. But that's the thing that I condition. Make sense? This road was blocked. This was blocked. This is not conditioned on. Right?
So they are not.
So I cannot go here, but I can go here.
So they are not independent.
So the answer to that is no. Yeah. Okay, so so let me give you a little bit of theory. So we have half an hour. So these two are basically equivalent way of saying the same thing. So if I say that D1 is family of all distribution that satisfies the Imap of a given graph, if that's one statement, and the second statement is that I have a graph, and I wrote the factorization based on the graph. Is the two statements are clear? What those are? So I've given a graph, and I somehow come up with a way to write all of this. It's a very tedious way, but I wrote this Imap of the graph. That's statement one. And the statement two is that I've given a graph, and I wrote down the factorization, which was very simple. Right? These two are equivalent. This is much easier to do than this. Right? Because for this I have to enumerate all of the possible subsets, and this was 2 to the power of n cubed. And it's hard. For each of those I have to run a baseball. Right? So, but this theorem said like, okay, forget about that. You have a factorization, write the factorization, that's the same. So we have a notion of soundness, that's the one that I just told you, that for a specific parameterization of the probability that satisfies a graph, the set of the Imap of the graph is a subset of the probability distribution by a specific probability distribution, because you can always fabricate specific distribution if you play with the parameters, like the example that I gave you. This is why for a given probability for a given graph, the Imap set of independence induced by the graph are a subset of the independence that are in a probability. But what about the other way around? We saw the example, right? The other way around is not true. You can always come up with specific weird parameterization that introduce new independents that are not in your graph. You saw that when I have examples like this, right? The I of the G was empty, but I played with the parameter in a way that introduced independence. So this is why it's the subset of the specific parameter. So there's a formal way of saying that. So we are saying that almost surely, so I'll tell you what almost surely is in maybe a couple of minutes, because that's a deeper concept than, say, a couple of minutes, is that we are saying that set of independence of the probability distribution on the graph are the same almost surely. So when you say almost surely, is that like almost everywhere except for very, very, very weird cases that happening with probability 0. So how many people have taken analysis? Oh, so that's so basically for the people who know analysis is basically a subset of that, like the measure of those are 0, right? So it's not that there's a set of parameterization that you can wiggle and still have IG a subset of V. So as soon as you change the parameters, you just get out of that set. The measure of that set is 0. Another important thing is that I think the last theorem that I have for today is that if a G is a Bayesian network and X and Y are not de-separated given Z, then there is some distribution that P is factorized over P. So I won't go through the detail of that. It's just for completion. Another question that we have is that what about the uniqueness? So here are 3 graphs. So four graphs. X and Y causing the parents of X3. There is a common cause. There's a chain, and there's a reverse chain. Right? So which of these satisfies this? X is independent of X2, conditional of X3. Which of these 3 satisfies that? B, C, okay, yeah. So basically A is the one doesn't satisfy it. Right? And you can show it. It's very simple. So you can write the probability distribution, the joint probability distribution that is coming from, let's say, one of them. So, right? This is a factorization induced by this. Is X2 given X3, X3 given X1, and X1. So this is a factorization induced by this guy. I can absorb these 2, right, and get X3, X1, right? I can write this as X3, X1, right? It's just a chain rule. I haven't made any assumption. And I can use a Bayes rule and say that, well, what is this? So this one is P X2, X3 divided by X3, right? By the Bayes rule, right? Agreed? And so this is this term, and this is this term. So what is this? By the Bayes rule, this is X1 condition on X3. So what did I get? So I can also decompose this guy further by just a chain rule, no assumption, right? So I can write this as X3 given X2 by X2. So I have Px1 multiplied by this term. So, and this, I'm going to get this. So the take-home message from this slide is that these, from the point of view of Imap, these 3 graphs are equivalent. Right? So this is why I was emphasizing that from the point of view of the Imap only gives you a specific parameterization, a specific family. doesn't give you specific distribution, right? If you are searching for, so let's say that you're a biologist and you want to say that, does X cause X1 and X2, or there's a chain that first X1 happened and then X3 happened and then X2 happens, you cannot distinguish between these three because they are equivalent. And this has very important implication in application whenever you, for example, want to find out the causal chain, if you want to interpret this causally. So this is basically a warning that don't interpret this necessarily causally, unless you have extra evidence that you can break that causal chain. All right, so we say that two Bayesian network G1 and G2 over X are I equivalent if their Imap of those two graphs are equivalent. And we can always find a specific probability distribution that introduces extra weird. So in the interest of time, I'm going to skip this one. So let's go to some practical examples. So people can have 3 minutes break and then go back to practical examples.
What is your measure on the set of distributions that are on the general set of distributions that then you say it's of measure 0?
Measure 0. So let's, for simplicity, assume that the measure is defined on a parameter.
Okay, so we are already in a parametric setting.
You parameterize just for simplicity.
Okay. Okay, and then you're saying no matter how you put the measure, there's...
Well, you can always come up with a way that for one setting,
you
introduce extra weird things.
Yeah.
As soon as you wiggle it a little bit, you just get out of it. Because that set is measure 0.
But the claim is that no matter what the measure over the parameter is, the set of the ones that would be unfaithful is going to be of measure 0.
Yes.
Okay. It's quite strong.
It's very strong.
Yeah.
But I don't prove or anything. You can go to Daphne's book.
Okay.
Because I guess if you want to prove it for the most general case, it's going to be very tough.
Yeah.
Because you cannot say that the specific, for a specific parameterization, probably a better way to prove it, I guess, is that you resort to functions. Instead of all probability distributions, it's functions.
Okay.
Measure 0 there, so there's no parameterization. But it's going to be quite complicated.
Okay.
So we're going to start again in 30 seconds. Okay, let's get it started. So we talked a lot about Imap, probability distribution, independence, and the V structure and all that. So what are the practical examples? So here are some examples of how we can define probability distribution and how give it the value and do sampling and so on and so forth. So this is a very simple way, I guess, like I showed you this graph a couple of minutes ago. So for a discrete probability distribution, the way that we can parameterize this is with basically a bunch of tables. These tables represent how this conditional works. For example, the parameter C here, the random variable C, is dependent of two random variables A and B, that each of those are binary, right? So these can take 2 values, this can take 2 values. So the table for this guy, condition on this, is going to be a table that goes over all possible configuration of the parent. So what if the parents are both 0, one of them is 1, the other one is 0, and so on and so forth. And so it's going to be column sum to 1. So one thing that I have to say here is that, okay, so let's, so of course the size of this is going to be So let's say that this has 7, this has 7, and this has 5. What is the size of this? 49 by? Say it loudly.
49 times 5.
Okay, so of course this is different configuration of the parents and different values that C can take. So there is no specific convention that you just put the parents on the rows or columns, just stick to one, and when you are implementing it, make sure that you don't confuse yourself. Well, one of them is row-wise, the other one is column-wise. So this is for discrete random variables. For continuous one, the conditional independence is basically a function that has a property density. So here, let's assume that A is a normal distribution with some parameters mu and sigma, is a multivariate Gaussian, and C is, I just defined it as A plus B conditional on some other parameters, right? So defining this conditional probability distribution probably for continuous is just basically probability distribution that depends on the parents. So it's most simplest Bayesian network is basically a case that all of these observations, so there's a convention that we always show the random variables with circles, and whenever it's observed, we show it with the gray, and whenever they're unobserved, we show it with the white circle. So we can view that. You can also view a parameter as a random variable. So this might be a little bit advanced, but let me give you an example that. So do we have any statistician in the audience? Yes. So what do you think that? So theta can be parameter, right? And can also be random variables. So what is the difference between them if I view it as a parameter? If I view a parameter which is free as a random variable, what would happen?
Get the posterior distribution.
Say it again.
Then you have a posterior distribution. You will need a prior for theta.
Okay.
That's a Bayesian of.
Yeah. So what if I say that it's free, it can do whatever it wants? What kind of prior that would be?
Uniform.
Good point. But so uniform is limited in a box. If it is
Flat distribution.
yeah, it's improper, right? Okay. So this is basically a view that you can still view parameters as quote unquote improper priors. So of course, whenever you have a lot of random variables, showing that as this way might be confusing. So we have so-called plate convention that whenever you have n random variables, you just put it in a box that this box represents that is repeated. It's basically shorthand for the things that I showed you earlier. And because theta is not going to be repeated by all of them, it's outside of the box. So we're going to use this probably quite a lot. So, of course, so you can use this plate model and then connect the different blocks. I told you at the beginning that one of the ways of building this graphical model is to view it as a template and then connect different areas, connect different things together. So let's say that I have a clustering problem, and these are my observations in 2 dimensions, right? It's 2 dimensions. So what is the assumption of the Gauss? What's the assumption of the mixture? So can we come up with a way to encode the mixture? It's basically a causal chain. So that or a generative sense to make a mixture. Anybody wants to answer this?
First, we choose which cluster it belongs to.
Okay, so let's call that Z. We get some from categorical distribution with some density that says that which cluster. Okay, then?
Then for each cluster, we might have a different distribution.
Okay, so for each of the, so let's call the entire thing Y, and just Y is 2 dimensions, right? So Y can come from some distribution that has parameter of ZK. So it's called ZI. right? So zi can become one of this value of 1 through k. So in this case, k is 3, right? And theta is just parameter of the cluster. So this is, let's say, the theta 1 is the mean and the variance of this cluster. This is the theta 2 is mean and the variance of this one, and so on and so forth, right? So we first get the cluster index, and you generate from the cluster specific distribution. So a way to show that is that, so y is dependent on z. And you have n of these, right? So you put a box around it that all goes from. Where should I put the theta? Inside or outside? Anybody? How many people think inside? How many people outside? Okay, so watch it. Is it either inside or outside? If I put it inside, I have to put an index. But this z is not going with the number of variables, only 1 through k. So I need to have theta 1, theta 2, theta k, and should be outside because they are not indexed by these plates. They're outside, so they have their own plates. So that's basically mixture model, but you can view HMM as an extension of mixture model. So you can think of HMM as, this box means the repetition of this structure, right? So you can view the HMM as this structure, as each of those are one of these structures, right? But they're connected to encode the relationship. So you can view HMM as an extension of the mixture model with extra arrows. Yes?
How do you represent that the theta is chosen by the value of z?
Well, how can I represent it?
Or, I mean, is it not represented, or how do you keep track of something like that?
So here I have to say that y is conditioned on z, yi is conditioned on zi, and the theta, right? Do you agree? So because to generate y, you have to know which cluster is coming from and what are the parameterization of that. So how does the CPD should look like? So the conditional probability should look like y condition on z and theta. And you pick something for this based on your problem. It's basically how your data generates semantics.
Can't you have a chain?
Huh?
Can't you have a chain? Like
Chain?
z, theta, and y? So theta is dependent on what z you get, and
Well,
y
no, it's like theta is independent of z. So z is just generated by some pi, right? I should have put something here. Make sense? Or no?
Oh, so the theta that
Yes.
But the only way to represent the fact that it's not just theta, it's theta sub zi, is in the parameterization. You don't represent that in any way in the graphical model.
Well, it's representing the graphical model, right? So let me, we'll have maybe, okay, let's spend time and do this properly. So I'll show you here. So in this case, I have z, right, which is index of the graph, which is index of the range. I have x, right, and I need to know the thetas, and there are k of them, right? So to generate x, you have to know z's, and you have to know all of the thetas. You have to know all of the thetas. And z says, should I choose this one, or should I choose this one? So it's already encoded. All right. So I guess we have enough. Thank you.